And so in the previous video, we talked about an example where we were flipping coins, and we started with only flipping 2 coins, and eventually we thought about the case where we were flipping an infinite number of coins. Right. And so, just to reiterate the lesson from the last video, as the number of coins in our collection that we were flipping approached a limit of infinity, the trend that we saw was that only a tiny fraction of macrostates relative to the total number of total multiplicity, only a tiny fraction of those macrostates have a reasonably large probability. Okay? And so that example focused on coins, but really, the concepts that we discussed there apply to molecules as well. Okay? And so, what we're going to do in this video is now we're going to go through an example where we're just considering a collection of molecules. So just kind of generic gas molecules. Okay? All right, and so what we're going to consider is a gas composed of monatomic gas molecules. Okay, and so when I say monatomic, I mean, for instance, a gas where you just have a single helium molecule or argon, right? Where it's not bonded to anything, it's just the atom by itself. Okay? All right, and what we're going to consider is the case of an ideal gas. Right? I know this is something you've talked about since high school, but I want to kind of revisit what is the definition of an ideal gas. Okay? And so whenever you apply the ideal gas model, you're implicitly making a couple of assumptions. Okay? And so for an ideal gas, when we say ideal gas, what we are actually saying is that we're considering a system where the gas molecules don't interact with one another. Right? So they don't see one another. One molecule can't tell that another molecule is around. Right? It doesn't interact with it. And also, each of the molecules themselves don't actually take up space. And so we're actually considering gas molecules that are what we call point particles, where they actually have no size, they have no length, they have no width, they have no height. Right? And in addition to not having any actual size, in our system, in our ideal gas system, we're also allowing particles to overlap one another. Right? If one particle is at a coordinate of xyz, it's okay for another particle to be there. Okay? Right? They don't take up space, and so you could jam as many particles as you want in that same xyz coordinate. Okay? So, based on this description, this doesn't really sound like a physical thing that could happen, right? We know molecules take up space. But specifically for the ideal gas, these are the assumptions that we're making. Okay? All right, so that's what an ideal gas model assumes. All right, and so with those assumptions in mind, let's now go through a thought experiment where we just think of how a single ideal gas molecule we're going to think about a single ideal gas molecule in a container. All right? And what we want to think about is how many different ways this ideal gas molecule can arrange itself in a container with some volume V. Okay? Alright, and so let's consider some volume. Looks like this. And in this volume, we could kind of split it up into different compartments. So let each of the squares in this volume represent some different XYZ coordinate. Okay? Alright, and so what we want to think about is, how many different ways a single ideal gas molecule can arrange itself. All right, and so if we just put one molecule in the system, this gas molecule could be at this point, or it could be here, or we could put it 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 here, here. It could be in any one of these compartments, right? Okay? And so when we think about, how many different ways the molecule can arrange itself, or otherwise, if we think about what is the multiplicity of how this single individual molecule can arrange itself, right? So I'll say multiplicity for one molecule. The number of different places that we could put this gas molecule, just one gas molecule, that's going to be related to the volume of the system. As in, if we increase the volume of our system, that means there's going to be more places that we could put our particle. Or if we decrease the volume of our system, then the number of places that we could put our particle would decrease as well. Okay? And so when we consider the multiplicity of the different ways that we could arrange the molecule, if the number of different places that we could put it is related to the volume, we would say that the multiplicity is going to be proportional to volume, right? So multiplicity will increase if we increase the volume of the system, and it will decrease if we decrease the volume of the system, right? And so the volume of the system, that's one thing that's going to affect the number of different ways we could arrange a single gas molecule in our system, right? And so that's, all we're considering there is just like the spatial coordinates of our system. But what we also need to consider is, the movement of the gas molecule as well. And so gas molecules, they aren't static things, right? They aren't frozen in place. Rather, they're busy moving and zipping around all the time, okay? And so, this molecule, it could be going in this direction, or it could be going in this direction, or it could be going in this direction. It could be going in that direction as well, okay? And so, depending on, what direction it's going, we can also consider that as another way that the molecule can arrange itself, right? Because a molecule going this direction would be different than one going there, okay? All right, and so the multiplicity of the molecule in the system, it's not only going to be proportional to the volume of the system, but it's also going to be proportional to the number of different ways, number of different directions that the molecule can be heading, okay? And so, to roughly describe this, the number of different directions that the molecule will be heading, we can consider what we call a momentum volume. Right? So it's a bit of an abstract thing, but essentially all it's doing is just describing, what are the different directions that our molecule can actually be heading. It could be going here, or it could be going here, or it could be going here. Okay? And so we just kind of call that a momentum volume. And for units, this momentum volume, it's going to have the same units as momentum. And volume, of course, has the same units of volume, so meter cubed. Okay? All right, and so you'll see that, the multiplicity of how we can arrange a single molecule just within our system. I said it's proportional to these things. But multiplicity, all that is just the number of different ways we could arrange the molecule in the system. And so this needs to be a unitless number. All right, and so we see that volume has units of volume, and volume has units of momentum. And so if we want to actually calculate omega, what we need to do is we need to divide it by a factor known as Planck's constant. And all this does is it gives us, so Planck's constant is kg m squared over seconds. And so if we cube that and then use it to divide out this stuff, it'll cancel out all the units. And so Planck's constant is just there to get the units right. So you don't have to worry about it that much. Okay? All right, and so the multiplicity of, the number of ways you could arrange a single molecule inside a system of volume V that could head in, different directions follows this. Okay, so that's for one molecule. If we are now considering the case where we had two molecules, it would be very similar, but essentially what we would be doing is we would be squaring the whole thing. And the idea behind that is because if we had, another molecule, based on the ideal gas law, the two molecules don't interact with one another and they don't overlap one another, and so they act independently. Okay? And so, as you may know from your stats class, if two things are acting independently and you want to calculate the number of different ways you could arrange them, all you have to do is just multiply those two things together. Okay? And so that's essentially what we did here. We just took the result of the multiplicity for one particle and we just squared it to get the multiplicity of 2. But there's one other thing that we have to do here. And so the particles we're considering, it's not like the coin example where, we're looking at a penny and a quarter, all the different coins were different. Here, what we're considering is just two molecules that are basically identical, right? If they switch places with one another, that would essentially be the same sort of microstate. Okay? And so what we got to do is to make sure we're not double counting microstates, all you have to do is just divide this result by the number of particles that you have, so 2. Okay? All right, so that's, just to reiterate, accounts for indistinguishable particles. Okay? All right, and so that's the result if you have two molecules. And now what we want to do is we want to generalize this for the case where we have n number of molecules. Right? And so for n molecules, the way we would calculate the multiplicity for n molecules, you could probably sort of see the trend that we're heading in. But what you would have is a formula that is, v to the n divided by Planck's constant to the n times that momentum volume to the n. And then to make sure we're not double counting things, we would divide that by 1 over n factorial. Okay? That's the general formula that you would use. Okay? All right, and so volume, that's, a pretty basic concept. That's just how big the system is. The number of particles, that's n. Planck's constant, that's just, once again, just to get the units right. That's the only reason it's there. But this momentum volume, it's still a little bit abstract, right? And so if we want to gain a little bit more insight, we need some way of calculating it. Now, modeling this momentum volume is way outside the scope of this class. It's actually a bit of a complicated thing. And so what I'm going to do is I'm just going to tell you the final answer. Okay? And so for our momentum volume, it's going to be described by this term right here. Two, and then multiplied by 2 times m, which is the mass of the molecule, right? Because if we're talking about momentum, the momentum is going to be related to the mass of the molecule. All right? And then it's also going to be related to the internal energy of the molecule as well. Right? And then internal energy is essentially describing, how fast is this molecule moving at the microscopic scale. Okay? So, there's a lot of steps that went on at this part, but at least for just kind of understanding, what this equation is telling you, this is sufficient. Okay? All right, and so if we kind of rewrite our multiplicity formula for these molecules, we could rearrange everything. And what I'm going to do is I'm going to pull all the stuff that's like a constant to the front. And then here, put v to the n, and then that internal energy. Okay? And so all this stuff is a constant, and to avoid having to write all that, we just call this constant alpha n. And so our multiplicity is alpha n, v to the n, 3n over 2. Okay? Right? And so, the number of ways that we could describe, the number of ways we could arrange n number of molecules in our system, right, just kind of follows this fairly simple formula for an ideal gas. The last thing I'll point out, you may be wondering why there's 3 halves here. That's a whole different story, but essentially the 3 halves is what you get if you're dealing with a monatomic system. If you had a diatomic system, so like nitrogen, so N2, you would have 5 halves, and so on and so forth.